So thank you very much for the invitation. It's very nice to be here virtually to talk to you folks about deep learning and the mysteries of deep learning and what we're doing to try to open the black box and understand what the machine has learned so that it can inform human physics. Now, there's a lot of people who have a lot of different opinion about what machine learning is, what deep learning is, and you see in the popular media, there's a lot of discussion. You see it in mathematical circles and computer science circles, and now, of course, it's very widespread in particle physics and in many realms of biology. Now, since we're all physicists here, of course, our goal is to use machine learning or whatever tools we can to unravel the mysteries of the universe. Our goal is to extract as much information as possible from the detectors that we build and we operate. And so from that point of view, we have a lot in common. I'm a physicist who works at ATLAS, so I'm a collider physicist rather than dark matter direct detection or underground experiment. And as of course you know, we have proton beams that smash together very high energy. But we take these very complex pictures of our data. We have millions and millions of events, but most importantly, each event is very high dimensional, meaning we take a lot of measurements of every event. And we have long suspected in our field that there's a huge amount of information hiding in our data that we are not using. Information that we could be using to help reveal some of the deep truths that we're hoping to uncover, but that has been missing for us. And a special focus of our energies at colliders are these objects we call jets. So when you produce a quark or a gluon, for example, any colored object, it will shower and give you a huge stream of particles, which will hadronize and deposit energy in our calorimeter, which is finely segmented. And the goal then is to understand these jets and to understand the process which produced the quark and the gluon. But we have very limited information because we only have the energy deposit in the calorimeter and the tracks. And these objects are typically not very well measured. And so there's sort of an obstacle to us to understanding the actual collision and what happened. So they've been a great focus for us in machine learning to try to improve our understanding, given the data that we measure, about what's actually happening at the underlying level. And we wrote a paper a few years ago talking about using deep networks to try to understand different kinds of jets. And this is a field we call jet substructure, because we don't just look at the jet entirely and say, here's a big stream of particles. We try to look inside the jet and understand, are there variations in the energy deposition, and can that tell us something about the particles that produced the jet? For example, at the LHC, we have unprecedented amounts of energy available in our collisions, which sometimes produces objects at very high PT. And when very high PT objects decay, their decay products are collimated. And so, for example, here in a top quark, if you have a top quark produced roughly at rest, its decay products are isotropically distributed, and so are often well separated, and you can resolve them individually. When they're produced at high PT, then their decay products are collimated, they can overlap, and so in a single jet, you may have quarks or the decay products from multiple quarks from a W, for example. And so this has been something we've been trying to understand using machine learning, and here's an example. So we take just the information from our calorimeter. So imagine our calorimeter is a cylinder that surrounds our event, and then we just unroll it and treat it like an image. And so here on the top left, you can see an example pattern of energy deposition from a single quark that's fired at the calorimeter. And there's some spray of energy there. On the right is a single example from two quarks. So here you have a W, a high PT, so two quarks are close together, and they leave two splashes of energy. Now, from a single example, it's very hard to tell anything about these jets. And so on the bottom row, you see what happens when you average over 100,000 events. And then we do some pre-processing and some rotating. And what you can see is that the quarks on the left tend to have a lot of energy deposited in the center, and it's basically just a cone that falls off as you move away from the center. Whereas the Ws have two locuses of energy, two places where the energy is deposited, which represents the fact that there are two quarks here. So on average, there is some information here. You can tell the difference statistically between a jet that came from a single particle and a jet that came from two particles. And this is very important for us to understand, is this jet a W, or is this jet a B quark, or is this jet something else? But as you can tell from the top row, individually, it's very difficult to tell them apart. So it's a good test bench for deep learning. Can we learn to tell quarks apart from Ws just using the calorimeter image? Can we train a network to do that? And especially interesting problem because it's very mature theoretically. Like the QCD physics that underlies the processes here have been thought through very carefully. And there's decades of literature inventing high-level features, features that are designed by QCD theorists that say, here's a quantity you can calculate on your image that we suspect will help you separate because it motivated from the underlying QCD physics. They understand the splitting of the quarks and the typical relative energy involved, etc. And so quantity number one here you see plotted on the top left is just the mass of the jet. W is a massive particle, a quark is low mass. So a massive particle tends to have the energy distributed at higher angles. And so you can see the difference between the solid red, where you see the peak of the W mass, and the solid blue, where you see jets just from quarks that tend to have much lower masses. And then we do two cases there, with and without pileup interactions. It's not critical. The thing to understand from this slide is that there are several high-level features that encode physics knowledge that are powerful discriminants already. And that gives us a good benchmark. It says, well, can we do better than the fancy intelligent theorists and their decades of thinking? So what we do is we train a network that combines all of the best features from the literature. So this is this blue solid line here, BDT expert. And it's a boosted decision tree, but a neural network does just as well. And it combines all the information from the existing literature and gives us a discriminant to try to distinguish between jets that have just a single quark in them and jets that come from a W. You see the performance in the blue line here. And the axis is signal efficiency on the x-axis and background rejection, which is 1 over efficiency on the right, on the y-axis. And so as usual, you want to be in the top right of this plot, and a line that's closer to the top right corner is better. So the performance is pretty good. Now, if we use the image network, and the image network does not have access to the high-level features, it just gets the images, just trained using convolutional networks on those images. It slightly exceeds the performance of the expert features. And notice that this is a log plot on the y scale, and so it looks like a small difference, and it's not an enormous difference, but it's real and it's statistically significant. And so this is the kind of thing we see often in our data. We see that a convolutional network or a very complex deep network can match or exceed the performance of well-understood, well-conceived, physics-defined features. And it leads us, of course, to ask this question: what has the machine learned in this case? And even if the performance were the same, even if they were totally equivalent, we would wonder, has it rediscovered those things? Or has it found some totally different strategy? Is there another approach? Is there something we've missed? You can imagine that in the case that it strongly exceeded the high-level performance, you would wonder, is there some nugget of information that we're missing? Is it possible that it could discover, just by deep analysis, some way to separate it, and that we could then interpret that, we could learn some physics from the network? And you might say, well, let's just look at what the network is doing. But of course, the network operates on very high dimensional data. I mean, these images are 30 by 30, which makes a 900 dimensional space. And so you'll see papers in the literature where people try to analyze a network, and often they try to plot the performance of the network as a function of one of the inputs. But in a very high level, in a very high dimensional space, this is essentially impossible. And it's hard to get any physical intuition for what's happening in this data. And also it's impossible to model. Like, are these images accurate? Could I use this network on actual data from the collider? Certainly not without validating that the modeling is correct. But but modeling, but validating 900 individual dimensions is very difficult. And then you have to take into account the fact that there are correlations. And so the dimensionality of this data makes it essentially impossible to verify the modeling or to get any insight into what it's doing. And this, of course, is why we typically boil down our information into high-level features. We do things like tracking, we do things like clustering, like dimensional reduction using physics-motivated heuristics is the name of the game for decades, right? We take low-level data and we use expert physics knowledge to turn it into high-level information. This is what physics is, right? It's interpreting our data in terms of our thought patterns. The problem, of course, is that deep learning tells us there's an information leak here, that there's some information in that low-level data that we are not using, that we have not captured, all right? Now, of course, we prefer to use high-level data for many, many reasons. Number one, it's easier to understand. And we should never lose sight of the fact that we are doing physics by humans and for humans. This is not some weird corner of the internet where bots create videos for other bots to watch, right? We're doing this because we have questions about the universe. We want answers. So nobody wants to plug their machine into a neural network and have it write papers, which are then automatically published for other neural networks to read, right? We need to be in the loop. And more importantly, we can't really verify the modeling of things that we can't understand. We can't define uncertainties sensibly if we can't understand them. And then just from a pure efficiency point of view, I would much rather carry around 7 compact features than 900. It's just simpler to do. And so the goal is instead of using neural networks which operate on low-level data as a tool in our analysis, use them as a probe, use them as a way to tell, is there information missing? So the first step would be the same, use machine learning, deep networks on low-level data to understand how much information is there. And then instead of using that as a final product, use it to motivate the definition of new high-level variables that have, we hope, gathered the insight extracted by the machine learning approach. All right, well, that sounds like a wonderful thing. How would you do it? How would you learn the physics from the machine? How would you open up this black box? So we have an approach here that we've developed in a recent paper. And the idea is to first define the complete space of possible ideas. I think of this the way I think about talking to alien physicists. Imagine aliens visited and they brought their scientists. How would you talk to them about particle physics? Well, the first thing you'd have to do is define a common language, and you'd hope that maybe they use mathematics and you could use Lagrangians, et cetera, et cetera. Now, here we have something of an alien intelligence, artificial intelligence, but we get to define the terms. So we're still in charge, and so we get to say, speak to me in a language I understand. And so we went and we talked to some QCD theorists about jets, and we said, could you create a complete space of all the possible ideas which could be relevant to this problem? And of course, they could make a mistake. They could be wrong. Their space could be poorly defined. But if we map the network into this space, if we use the space to define the set of ideas, then it tells us something about the definition of the space. If the space fails, then we've learned something about what theorists think about how to define this space. All right, so first we define the space of ideas, and then we try to map the network into that space, right? And we need to think about what it means to map that. So let me go into a little bit more detail about how each of these steps work. First, how do we define the complete space of ideas? Now, this is not a general, for any given problem, you may need a different space of ideas because every task is different. But for the space of jets and understanding things in our calorimeter, we have these quantities that are called energy flow polynomials. And they're a complete set, meaning that any observable should be included in this space. And they're built on point-to-point correlations. And so you perform a sum over elements in your image, take a single point, for example, a single cell in your calorimeter, and another cell in your calorimeter, and you calculate these quantities, these z's times these thetas. And the z's are essentially the PT of that cell, the energy deposited in that cell raised to some power. And then the thetas reflect the angular information, the angular distance between them. And so you could construct these graphs that show you sort of pictorially how these calculations are, where the lines represent angular calculations, and the dots represent how many cells are being included. And so this graph, for example, is a 3-point correlator, uses 3 cells in the calorimeter and does these powers of the angles. And so according to our theory friends, this is a complete set of spaces. You have zillions of these graphs to define any arbitrary calculation you might want to do on these quantities. And all of the high-level features that have already been created exist in this space, can be expressed in terms of these kinds of polynomials. All right, so we have a language, we hope, which means something. If we could map our deep network into this space, we could then go back to our theorists and say, the network is using this graph and this graph and this graph and this graph. And what does that mean? What is the physics of that? It should say something to us. All right, so how do we map it into that space? It's not trivial to compare 2 networks. It's complicated because, you know, any nonlinear one-to-one mapping of the network doesn't change the performance. Right? If you imagine how you actually use a network, you typically put a threshold on it and say, above this, I'll call it a signal, below, I'll call it background, or, you know, whatever classification task you have for it. And so really what you're interested in is not the actual value, right? Because these nonlinear mappings can change the value without changing the actual performance. What you're interested in is the decision ordering. You're saying, if I have 2 points in my space, do 2 networks give the same ordering of those 2 points, right? And so is one point X is considered more signal-like than another point X prime. And we claim that if 2 networks, or 2 arbitrary functions actually, give the same decision ordering for all pairs of points in your input space, then they are effectively the same neural network, or the same decision function. They're using the same information, they have the same set of decision surfaces. Imagine scanning over the output of your network with various thresholds. Each one defines a surface in your input space that says above this, it's signal, and below it, it's background. So if the decision ordering is the same for the 2 networks or the 2 functions, then they are making the same decisions, they use the same information. So that's how we define the mapping. We say that if we can find a point in this space that makes the same decision ordering as our network, then we have mapped it into that space. All
Hi,
right,
Daniel,
so,
a few minutes warning.
Yes. I'm sorry, was there a question?
Oh, sorry, that was a few minutes left over warning.
Okay, great. So the question is then, we have 2 questions we'd like to ask. Is there a missing thing? Like, is the network doing better than our existing ideas because it's found something new? Is there one idea we can add to our list of features that will close the gap with the performance of the network? And the second is, could we start from scratch and rediscover these features? Could we start from scratch and find a new approach to understanding these jets? So we tried the first one first, finding a supplemental feature. And so what we did is we said, we're interested in comparing the performance of our network, that's the thing on the left here called BVN for black box network, to our network of high-level features, so that's HLN. So we created a bunch of signal background pairs, and we asked, do they make the same decision ordering? Again, not is the value of their output identical, but do they order these pairs the same? And we found some that they order the same, and we put those aside, and we focused on the ones that they order differently, because this is where the information is needed. This is, if we're going to understand what the black box network is doing, we're going to focus on the cases where it's making a different decision than our existing features. Then we searched through our space of possible ideas and found the one that had the highest decision ordering when compared to the black box networks in this subspace. So we said, let's focus on this subspace and find a new bit, a new piece, a new tool, which can help us align best with our black box network, the deep network. So we found one, and the idea is then we would feed it into a next generation of our high-level network. So we found one. It's this feature here. It happens to have it happens to look like this graph, and the exponents of the PT and the angle are 2. And on the left, you see the distribution of signal and background from this observable. So clearly it has power to discriminate. And that's over all pairs, all values. On the right, you see the distribution of signal background only in this subspace where it's where the other features disagree with the network. So this is the place where we need it. And you see that it still additionally has some power here. And so what we did is we plugged this network, we plugged this new feature into, with our other variables, the 6 high-level features, we combined them into a new network that has 7 features. And we see that its performance now matches that of the deep network, the convolutional neural network. They both have this performance of 0.953. So what that means is that we took the state of the art, which was these 6 high-level features. We had a certain performance. We found that the convolutional network exceeded that. And then we used the convolutional network to point us to another idea, one that we hadn't considered yet, which could close the gap with its performance. So we successfully sort of mapped what the network has learned back into the human space to use a feature that we could analyze, we could understand. So what is this thing? Well, this graph here has kappa equals 2. And remember, kappa is the exponent of this quantity we're calculating, essentially the PT of the cell divided by the sum of all the PTs of the cells. And for kappa equals 2, you have some non-linearities, which make this non-infrared safe. That is, when you try to do these calculations and you get to in considering emissions of very, very low energy gluons, some of these quantities are theoretically poorly behaved. And for example, if you implement them in Pythia, you may get a very different answer than if you implement them in Perlin. And so that's why these kind of things are typically avoided. The information in here is not necessarily something you want to rely on. It may not be well modeled in your Monte Carlo. And we notice that, and so here on the bottom, I have a table that shows you the top performing graphs. And the number 1 there is the one we chose, but it's a sort of a very smooth surface from optimization. The second best performing graph does almost as well. But all of the top 5 performing graphs have this feature. They are kappa equals 2. They're all infrared unsafe. So what that tells us is, yes, the network has found that we are not using all the information, but you shouldn't use that information blindly. You should understand that information, because in this case, it's probably not information we actually want to use on our data, because it's not typically well understood in our simulation. So then very quickly, we also said, well, let's back up and toss out all of those ideas. Let's pretend we had come to this fresh before the theory community had developed all of its fancy ideas. Can we rediscover those features? Well, we started essentially from scratch from a very small number of features. And we found that after 10 or 15, we could assemble these graphs together to reproduce the performance of the network without relying on the existing high-level features. And so that's certainly a larger number than 6 or 7, but it tells you that even without the guidance of the theory community, you could start from essentially scratch and boil down a 900-dimensional space into a handful of dimensions that you could then look at and understand. And if you look at some of these graphs, some of them make a lot of sense. They look a lot like the kind of features that theorists have already created. Cool. Some of them are weird. They have like high chromatic number. Chromatic number is the number of colors you would need in order to assign a unique color to any adjacent pair. So there's a kind of graph in here which are typically not considered by QCD theorists. They just thought that wouldn't be useful. They had some arguments they made that said, let's not consider that class of idea. But it turns out that the ideas used by the networks map well to these class of ideas. And so it points us in a new direction and says, you should consider these kinds of ideas. So my point is that while deep networks are very powerful, we should not be using them necessarily as a final tool on our actual data, but instead as a probe of the information. Say, is there something missing here? And if so, let's map it back into a space of things that we can understand. This allows us to be more compact. It allows us to describe systematic uncertainties on these quantities, to validate the modeling of the information going into our networks, and in some cases, potentially even reveal unexplored ideas or brush away theoretical biases that have shaped the structure of our intellectual investigation. All right, thanks very much for listening. If there's still a few minutes, I would love to answer any questions.
Thank you, Danielle. Alex, would you mind sharing, sorry, would you mind reading off the questions? And I remind people, if you have questions, please post that on the Q&A.
Right. So for
I
the
see. Okay, so there's
first question,
questions here.
yeah. How do you verify that what the neural network is learning from the LL feature information is real physics when that information is lost in the transformation from LL to HL?
How do we verify the neural network is learning what the neural network is learning from is real physics? Right, so the idea here is to map the low level into the high level. And then we can understand whether that's physics or whether it's just a baloney artifact of the simulation. I mean, when we map into the high level, then we can interpret it. And then we can say, oh, this makes sense. Oh, we should have thought of that. Oh, this is cool. Or this tells us something about jet physics. Or it can say, oh my gosh, look, it's keying off of this other thing, which we know is not real physics. So the idea is that mapping it to high level allows you to make that decision. Is this real physics or not? Is this something I want to include in my actual analysis or not? This is a really great question. Number two, is there a way to use a similar approach when we don't have a complete set of physical variables directly available? Certainly, I mean, you can always map it to an incomplete set. I think it's a little less powerful in that case because if you don't get a complete mapping, you don't have as much insight. Like in this case, imagine we didn't get a good mapping. There's no set of variables in our space which describe the network. That tells you something about the space, right? It says, oh, well, there's clearly an idea here which exists outside of the space. So maybe when you sat down to write the complete space, you made some assumptions, some implicit ideas that shape your thinking that you hadn't realized. That's powerful. If your space isn't complete, then you don't get a good mapping, then it might just be because your space isn't complete, which isn't very exciting. But if your space isn't complete and you do get a good mapping, you can still use it, right? As long as you find the answer in your space, it's still valid. Great questions. If you train with a different architecture, do you get the same high-level features back out? Oh, fascinating. If we train, for example, on the images with a different architecture, that's not something that we have explored. It's a great question. That's a great suggestion. Thanks. We'll look into that. It's not a question I have the answer to. Next question is, could the high-level feature be found from some limit of MC simulation systematic? I think this question is asking whether the high-level features reflect the fact that the simulation is not describing the data perfectly. Right? In this case, there's no data in this study. We're only analyzing what information in the Monte Carlo is being used by our network. And so I think the idea is to figure out if that information is something you think the Monte Carlo simulation models well or models poorly. For example, if there's something in your Monte Carlo that you know is poorly modeled, which exists for all Monte Carlos, and then you discover, oh my gosh, it's using that exact thing, then you'll know that you don't want to use your deep network and that you'd like to map it into a set of high-level features and then essentially cut that out. Because here you could prune, you could say, I'm going to map into high-level features, and then I'm going to remove the ones that I don't think are well described, are valid. Next question is, information loss in data may not be the only factor affecting performance. How would you quantify taking this? How would you quantify this, taking into regard the different techniques, BDT versus neural network? There's always a question of whether your machine learning technique is well optimized. Like there's the question of information loss from the data, and there's a question of have you optimized completely? And of course, optimization is an area where there's still a black box. It's still an art. I mean, you could take one student and give them the problem and give it to another student and get a different performance. Here we've done our best to really push these networks as hard as possible, using lots of different learning techniques and lots of different optimization strategies to make sure that we're really at the edge of the ability of a network that's limited by the architecture and the information that's going in rather than the optimization. But you can never know for sure. Could you use the same idea to do the opposite and determine if there are issues within your simulations? Yeah, I suppose you could. You could imagine mapping the low-level features to the high level and then studying those in your simulation by comparing the distributions in simulation and in data and saying, are these features well modeled? Like, say you get some new physics quantity nobody's considered before, and you're like, oh, that's interesting. Is it well modeled? Then you discover, oh, it's not. Well, that could tell you something about your simulations maybe you didn't know before.